I'm going to give you a little overview on batteries this evening. And this builds on a TNT program that I did, gosh, it's been 9 months ago or so. Kind of backed by popular demand, I guess, so I'm going to expand on what I said in the last meeting. One of the reasons I'm interested in doing this is, believe it or not, once upon a time in my past, I worked for the Gillette company. And at the time, Gillette owned the Duracell business, so my responsibility in Gillette was to manage the Environmental Health and Safety Organization. So we did a lot of work in the manufacturing facilities, and I got to know the guys in the R&D organization pretty well. And so I just had a kind of an interest in batteries because of that, but also because of my amateur radio hobby. So I'm going to take you through a little bit of battery history, and then a little bit about different types of batteries, but I'm really going to focus on batteries that are of interest to amateur radio. The other thing is I'm going to be up here with a little bit of humility because I had a lot of folks come up here and say, do you know about this battery and that battery? So for the, so I've actually, I would welcome any comments that anyone has or that anyone wants to build on as I go through this. So, all right, well, let's go ahead and get started then. So what are batteries? Batteries are composed of a couple of at least 2 electrochemical cells. So this is a battery because it has multiple cells in it, and this would be considered really not a battery. Everybody calls them batteries. This is a cell. So cells put together are actually called batteries. And it turns out that the chemicals that are in the battery convert stored chemical energy into something that's useful for us. Most batteries have some sort of a finite useful life, so a battery like this Alkaline battery is considered a primary cell. You use it once and toss it in the bin, and then these types of batteries are rechargeable batteries, but their life is finite. There's only a certain number of charges that each battery can have before it, usually what happens is the structure of the metals inside the batteries begins to break down. The internal resistance increases and they don't work anymore. So, with proper care, batteries allow us to operate off the grid for a while. They'll live a long life if you treat them well, and they're safe if you use them properly. We're going to talk about some safety issues with batteries, but if you use them properly, you won't have any trouble. So a little bit of battery history. It turns out that there's a big debate about this, but there is this cell called the Parthian cell that was discovered in a dig in the 1930s, called the Parthian cell, and the archaeologists who dug it up think it's this 2,000-year-old battery that was used in Iran, and there's a big debate about whether it was actually used for power, which it probably wasn't. More likely it was used for electroplating because they knew back in those days that people liked to coat objects with certain types of metals, and somebody figured out that this thing with a positive terminal, negative terminal electrolyte would actually do the job for them. But real serious battery work began back in the 1800s, and it's kind of interesting how it all began. So this gentleman, von Gurka, and then Alessandro Volta started out with spark generating devices. They realized that you could rub certain metallic structures. They found that electrostatic charges began to develop, and things like feathers and strings would stick to the metal, and then they began to discover that you could create an electric spark. And so one of Volta's first inventions, I think this is kind of interesting, is called the electric pistol. And the electric pistol was kind of a first long-distance communication device. It was not really binary, it was sort of monary, and what I mean by that is that Volta determined that if you filled the jar with methane, and then you put 2 electrodes in it and closed the circuit, you could communicate when the jar exploded. So he proposed to use this as a signaling device known as the electric pistol. So while he was working on the electric pistol, there was a guy named Galvani who discovered this phenomenon that he called animal electricity. And what he did was he got some frogs and hung a frog in an experimental chamber, and he noticed that if you touch the muscles of a frog leg with 2 different metals like zinc and copper, the muscle would start to twitch. And that was the result of a low voltage that was created across the muscle and causing the muscle to contract. And Volta heard about this experiment, and so he decided to begin to look at putting different types of metals together, and he found out that he could generate a constant flow of electrical power using combinations of dissimilar electrolyte solutions. So metal with two different metals with electrolytes, and he could generate power. And he also learned that if he stacked multiple of these cells together, that it increased the voltage. So it's really Alessandro Volta who really began to work with batteries back in the 1800s. So like these cells, was he really created the first battery. Okay, so rolling along then, in 1802, a gentleman named Cruikshank took zinc and copper plates, put them in a box, and filled the box with electrolyte. And then he soldered the metal together, and then he flooded these sealed boxes with brine and weak acid. And this really sort of became the first of the mass-produced batteries. It wasn't rechargeable. These batteries weren't rechargeable. They produced more energy than Volta's discs, but that began to get us on our way. The rechargeable battery came into being in about 1859. This guy named Plant invented the first rechargeable battery that was based on lead and acid. So the lead acid battery that we use today was actually invented back in the 1850s. And then a Swedish guy named Junger invented the first nickel cadmium battery. Didn't work too well, but that's the time that it was invented. And then Thomas Edison, being the great experimenter that he was, so this is Edison here. Plant and Junger. So Edison then began to experiment with batteries as well, looking at nickel cadmium batteries and iron cadmium batteries. Didn't have a lot of luck with the iron cadmium, but made some contributions to battery science. And then a couple of guys, Schlecht and Ackerman, invented a way to bind nickel to electrodes in batteries, and that really improved the capability of the nickel cadmium cell to generate a suitable amount of energy. And then this guy named Neumann produced a sealed nickel cadmium cell in 1947, and so that kicked off the age of the nickel cadmium battery. So it really wasn't until the 1950s, 40s and 50s that we began to get good rechargeable batteries. Then the modern alkaline battery, like these guys here, was invented by a guy named Uri, who was working for Union Carbide. So he developed did a lot of work with carbon zinc batteries, and then ultimately with the alkaline zinc batteries that I'll talk about in a minute. And then the environmental issues have kind of scuttled the use of nickel cadmium batteries, because if you toss nickel into a landfill, the heavy metals are of course quite toxic and cause water contaminations, which we like to avoid. And the Europeans really put an end to the use of nickel cadmium batteries in the 90s and the 2000s. And then since then we've had lithium technologies that were invented in the early 1900s, but not commercialized until about the 1990s, first by Sony. So real brief history, quick history of batteries. So haven't been around for a long time, and really rapid development since about the 1940s, 1950s. So what's in a battery? So the picture that I have here on the screen shows the structure of a typical alkaline manganese dioxide cell. So this is basically a Duracell battery or an Energizer battery. And what's in this battery, so these are the kinds of batteries that we used to make at the Duracell business where I work. And these cells have four important parts. The first is the anode. That's the negative part of the battery. The anode is this negative end here. There's a pin that runs up through the center of the battery. And in the center of the battery, it's filled with kind of it's an aqueous alkaline solution. It's a sodium potassium hydroxide solution that's thickened with some stuff called carbomer. It makes it like a real viscous fluid. And then in that viscous fluid is what's called spun zinc. So there's metallic zinc in the center. And this nail that's in the center makes the electrical contact with the zinc that's in this alkaline salt solution that has the zinc in it. Interesting story about the zinc is the zinc, it was made by Duracell. Duracell is one of the biggest users of, zinc in the world. And the spun zinc is very fine particles of zinc that are made by taking very large ingots of zinc. And we had literally smelters that ran in our battery facilities. And these ingots would get dropped into the smelter. And then, you remember the scene from the Terminator, you know, where the guy turned into metals and floated down the road. So in the smelter, we would have the melted zinc run down a sluiceway, and it dropped into a hole, and then hit a spinning plate at a certain speed. And when that melted zinc hit that plate, the zinc would spin, and it was set up so that we would have a distribution of zinc particles, metallic zinc particles, that were then used in the solution that is in the middle of the battery. So that's how the zinc is put in the center of these cells. Then the battery has a separator that isolates the anode electrolyte from the center from the cathode material, which is the manganese dioxide. And there's a paper insulator that separates the anode from the cathode on the inside. And then the cathode is the positive end of the battery. And then the separator keeps the electrons from flowing, and it allows, as I'll show in a minute, ions to move back and forth when the circuit is closed. So the current runs from the anode to the cathode, and ions are moving back and forth inside the battery. So that's the basic anatomy of a battery. Every battery will have an anode, a cathode, a separator, and an electrolyte. And as I said, a battery has multiple cells that are put together. So on the anode and cathode, the electrode that releases the electrons, as I've already said, is the anode, and the electrode that captures the electrons on the other side, the positive side of the battery, is called the cathode. So you can see how the current is moving around. You've got the cathode, anode with the electrolyte in between, and a separator between the anode and the cathode. The separator, as I said, isolates the anode from the cathode. It's typically moist with some kind of electrolyte. So in the alkaline battery, it's sodium, potassium, hydroxide, and in the case of a lead acid battery, for example, it would be sulfuric acid. So some type of a conductive electrolyte. It allows movement of ions from the anode to the cathode during discharge, and it insulates from electron movement. And then the electrolyte itself makes the battery conductive by allowing the movement of ions from the cathode to anode on charge and in reverse on discharge. And when electrons flow from one electrode to the other with some type of a load, the movement of ions occurs inside the battery through chemical reactions that I'll show you in just a second. And again, I've already mentioned some of the electrolytes that are present in these batteries. Okay, before I move on, any questions about sort of the basic anatomy of the battery? Okay, so let's move on. So what I'm going to talk about now is probably what's a little bit more interesting, or what are some of the ways in which we measure batteries. So the first one is that I want to mention is voltage. So voltage is the potential difference from negative to positive terminals of the battery. So batteries will always typically be marked with some kind of voltage. Get one right here. This is 9.6 volt battery. So that again measures the potential difference between plus and minus. And then the other thing that's labeled on a battery is its capacity. So the capacity is the amount of energy at the battery voltage that's stored to run the electronic device. And the units that are measured are called amp hours. It's amps times hours. So in the case of this battery, it's 2,000 milliamp hours, which is 2 amp hours. So what that means is that if you run this battery for at a rate of 2 amps, if the discharge is 2 amps, the battery will run for 1 hour at 2 amps. Or if you run it at 1 amp, it should run for 2 hours and so forth. So it's amps times hours. So the capacity on these batteries will vary. This is a 2,000 milliamp hour battery, and I'll talk more about this in a second, but just to give you a sense for what you can do, this battery is 6,600 amp hours. So it's a lithium battery that I'll talk about in a minute, but it stores in a very small package a lot of useful energy. And then there's a measure called internal resistance. I alluded to that just a second ago. The internal resistance, there's always a certain amount of resistance in a battery, and it results in a drop in the voltage when the battery is used. And internal resistance is dependent on the battery, its chemical properties, its age. And it turns out that measurement of internal resistance is a good way to determine the health of your battery, because as batteries get older, the internal resistance increases, and that's usually what kills off the usage of a battery, usually due to breakdown in battery performance. Hello, 1, 2, 3, 3, 2, 1. Shall I move this down?
No, it was just starting feedback on it.
And then the C rating on a battery, this is something that's usually of interest primarily to the radio control flyers, because what radio control guys want is a big blast of voltage from their batteries, particularly when they're taking off a helicopter or they're taking off an airplane. So the C rating is the output capacity in relationship to the total cell capacity. So a 10C battery for a 2.2 milliamp or 2,200 milliamp hour battery means that you can get a maximum current out of this thing of 22 amps. Or this one's a 35C at 6,000 at 6.6 amps. So 35 times 6.6 is a whopping lot of power that you could draw out of this thing all at once. So guys that are racing cars, flying airplanes, and so forth want batteries that have a very high C rating. So we'll talk a little bit more about that in a minute. So what do these parameters mean? So I just thought maybe that this concept of different sized barrels would help explain this. So voltage is, if you think about a 55-gallon drum, the voltage is represented by the height of the drum, and then the capacity is kind of a measure of the volume inside the drum. So in this case, I've got 1x voltage and 1x capacity. So if you then double the size of the barrel, it's like increasing the amp hour capacity by twice. But in this case, the barrel is the same height, so it delivers the same voltage, but it has basically twice the energy that's packed in it. So, so the voltage gives is the measure of the potential difference between plus and minus. But the amount of time, the amount of juice in a battery is the amp hour measurement. And then you can have batteries, of course, which have a higher voltage, but the same amp hour capacity. So there's all these different variables that you can play with whenever you buy batteries. So then the last piece of information I want to share with you before I move on to the different battery types is what's the battery market look like right now? And I thought this was interesting to see where batteries are being sold these days. So most of the batteries that are sold in the marketplace are lithium-ion batteries, which are used primarily in our laptop computers and our cell phones and so forth. So that's right now the biggest market. And then the second biggest market are the starter batteries. So these would be the lead-acid batteries that like you have in your car, followed by alkaline, which bazillions of those batteries are sold, which as a guy who still owns a little P&G stock, I'm happy to see. And then stationary batteries and so forth. So that's the rest of the market. But lithium has really taken over the market these days. So any questions on the battery structure, anatomy, how they all work, what the different pieces are, the different measurements before I get into kind of the different battery types then that we might use on amateur radio? And then I'll have a little show and tell to go with it then. Okay, great. So I'm going to talk about alkaline, nickel metal hydride, nickel cadmium, and then the lithium-ion batteries, lithium polymer, and close off with the lead-acid batteries. So alkaline batteries, good old Duracell. This is the typical mass market battery that we would all buy for putting in our flashlights and for all of our different devices. These are all throwaway batteries. The typical voltage, the nominal voltage in a Duracell battery is about 1.5 volts. Under load, the voltage will drop to 1.1 to 1.3 volts, and when they're dead, when they die at about 1 volt. And I'll show you some measurements on an alkaline battery in just a minute. So to give you a sense for how much power is in a battery, about 1.7 to 3 amp hours will be found in a typical AA battery. And again, I'll show you a pattern from that. The chemical reaction may be of interest to you. It's zinc plus manganese dioxide, like I mentioned. that generates the voltage of about 1.5 volts. So it's the chemistry that delivers the voltage that you get from the battery. Charge type. Most of these batteries you shouldn't recharge them. If you put them in a charger, typically they blow up. And that's not meant to, it's not by design. It's not something that Duracell, plans the obsolescence in. It's just the way the chemistry works and what the batteries heat up and they leak and they cause all kinds of problems. The power density, watts per kilogram. So they're pretty heavy for the amount of power that you get out of them. And that's one of the big issues for us when we used to ship these things. If you get a few thousand of these in a shipping crate, it's really heavy because it's a stainless steel case that's filled with zinc and manganese dioxide. So a lot of these together are really heavy. They're pretty shelf stable. Duracell guarantees these things to last for 10 years. I haven't tested that, but this thing theoretically is good until December of 2023. So hopefully I'll still be around when it's still good. And then the other thing that's really interesting about batteries and the Alkaline batteries is that they're really safe to throw away. And in fact, the most efficient way to deal with these things is to toss them in the landfill because there is really very little useful value in these batteries when they're done. About all you can do is grind them up and mix them with asphalt and use them to pave roads whenever you're all done. Because you can try to collect some of the scrap metal from it, but it's not very valuable. And in fact, in Europe, there are requirements that companies take batteries back. And in some countries, it actually costs more per battery for us to take them back and figure out how to use the damn things whenever they're all done, as opposed to just tossing them in the landfill. So environmentally, they're really safe, and the landfill disposal for the Alkaline batteries is a really good way to get rid of them. So I'm going to show a few discharge curves coming up just so that you can see kind of the comparison of how batteries behave whenever you use them. And so before I tell you what results we got here for this battery, I'll just orient you to what these graphs show. I'm sorry the text is a little bit small. There's not a lot I could do about it because of the output that I get from the device that I use to measure the batteries, and I'll show you that device in just a minute. But what's shown on the right-hand side of this plot is, sorry, left-hand side of the plot is the voltage. So what we've got here is a discharge curve for two AAA Duracell Alkaline batteries discharged at a 0.5 amp. And so when you put it under the load and discharge it at this 0.5 amp rate, what's shown down on the bottom is the amp hour capacity of the battery. So if you remember a little bit earlier, I said that an Alkaline battery is discharged at 1 volt. So if you have 2 volts in series, the discharge voltage is 2. So with this battery, you can see that these the total amp hour capacity of the two AA batteries is about 283 amp hours, or 283, sorry, milliamps. Sorry, 283 milliamp hours. So each one of these Alkaline AAA batteries has about 100 or so milliamp hours, and so it's not a lot of capacity. If you think about 283 milliamp hours versus 6,600 milliamp hours, it just gives you sort of a comparison of the difference in magnitude. So not a lot of juice in a little AAA Alkaline battery.
Are these in series?
Yes. Oh, sorry. Yeah, they're in series. So
wouldn't that just be the capacity of each one? I'll talk later.
Okay. Yeah. Actually, you're probably right. You are right. You are right. So that's each one has a voltage. Each one has a capacity of 200. Right. 200 milliamp hours. So you're right. Thank you. Okay. So anyway, it's still not very much. The point is still the same. It ain't very much. Okay, so typical uses of Alkaline batteries, we use them in all of our devices, flashlights, cameras, broad range of consumer products. They're not rechargeable, typically readily available. Now this next slide shows you one thing that I really, really dislike about Alkaline batteries, and that's this right here, is that in devices, sometimes they just leak. And again, you'll see these are Duracell batteries. Recently, I've had a lot of trouble with Duracell batteries leaking in things that sit around a long time and use just a small amount of current. So just keep an eye on these things. And you know, if you have like a GPS unit you're not using very often, take these alkaline batteries out because they make a real mess of things. Okay, so the next battery type I want to talk about are the nickel metal hydride batteries. There's all kinds of them that are available. Some of them are better than others. I just brought some examples here. These are some Energizer batteries. I got some from Amazon last summer before I went on a big camping trip, and I found these are pretty good. Someone, I think Ryan mentioned, these are Panasonic batteries, you said?
They're rebranded Panasonic analog batteries, which are really good.
So, you know, I used them on the camping trip. I charged up a bunch of them, and they work really well. And then, otherwise, I've just thrown them in this pot. So, I don't use them very much, but I have them for whenever I want to use, you know, for flashlights on camping trips and that sort of thing. So, anyway, nickel metal hydride batteries, the voltage is a little bit less than what you see from a typical alkaline battery. Their nominal voltage is about 1.25 volts. When you first charge them up, they have a little bit higher voltage. And then again, they discharge to about 1 volt they discharge to 1 volt. And sometimes if you over discharge, and it's one of the things you want to watch for, cause the polarity to change in them. So you want to be careful about draining them too far. The capacity of the AA amp hour battery can range anywhere between 1,300 and 3,500 milliamp hours. On this particular one, it doesn't show up really well, but this particular Duracell battery indicates that it's 2,450 milliamp hour capacity. So, and I'll show you in just a second, the capacity of these batteries typically is a little bit greater than a AA battery. One time I remember talking with an R&D guy at Duracell, and he said, you know, Leon, it's really difficult to innovate in the battery business when you're limited by the size of the can you can use in the periodic table of elements. So, you know, it's always a big struggle to try to, what the game is to try to cram as much energy in limited sized cans as you can. And it's all about tweaking the chemistry to try to squeeze a little bit more efficiency out of the batteries as you go forward. For those of you who are interested, I showed the chemical reaction here. I won't walk you through it. Different chargers. You should use a charger for a nickel metal hydride battery, not for one that is for a nickel cadmium battery. They like to be charged in different ways. So make sure that whatever you use is specifically designed for the nickel metal hydride batteries. Same for lithium batteries. Lithium batteries require a different type of charger than the nickel metal hydride as well. So you need to be careful about using the right charger. Self-discharge, a little bit higher than nickel cadmium. It varies with temperature. I find with these batteries that I need to recharge them every once in a while. If I want to make sure they're good to go, I just drop them in the charger and top them up to make sure that they're fully charged when I go on a trip. They last a long time. 500 to 1,000 cycles, and again, you can toss them in a landfill without any environmental concerns. So again, typical uses of these batteries, they can very, very much useful, just like you would use a typical alkaline battery. Broad range of consumer products. They're often found in electrical vehicles. The radio control guys use them quite a lot, or used to use them quite a lot. So from back in my early radio control days, these are a couple of examples of nickel metal hydride battery packs. I'll pass them around. You can see with these types of plugs, that was what we typically used for the radio control stuff. So those are dated like around 2005. I don't know whether they'll still work, but anyway, that was a typical power pack that we would use for electric model airplanes. They have greater capacity than a typical alkaline battery. And if you got really good ones, their energy density can approach some of the lithium batteries, you know, some of the canister style lithium batteries. And they have a lot more capacity than a typical nickel cadmium battery. Readily available, lots of low cost chargers are available with them.
So this is a discharge curve this is a AAA battery, 2 cells in series, just like I showed a little bit earlier with the alkaline battery. And to make the comparison a little bit easier, so you can see the difference between the capacity of the nickel metal hydride battery, which is right here, compared to that previous one that I showed you with the alkaline batteries. It has a difference. This test is about 275 milliamp hours. This is out to 354 milliamp hours, so a little bit more capacity in a direct comparison in the nickel metal hydride compared to the alkaline. So if you want your flashlight on a camping trip to run a little bit longer, your GPS to run a little bit longer, your better choice is the nickel metal hydride battery. Nickel cadmium batteries, I won't say too much about them because they're sort of a technology of days gone by. Again, just to repeat, the main concern with the nickel cadmium batteries is the environmental liability associated with getting rid of them. So you can't really toss them in a landfill without worrying about creating cadmium contamination. Fairly heavy for the energy that you get out of them. If you leave them sitting around, they do discharge. A lot of cycles available out, typically around 2,000 or so. And the other thing is that in my own experience, using them again back in my radio control days, and I actually still have an old ICOM radio that has nickel cadmium cells in it. I've never noticed this memory effect. You know, there's this concept that a nickel cadmium battery develops a memory so that if you only discharge it halfway, its capacity goes down, theoretically, or that's what we're told. Apparently that's a myth. I've never experienced that. It works if I've partially discharged and recharged. My nickel cadmium batteries have always maintained their capacity. So, again, probably not worth talking about too much because we don't use them very much anymore. All right, next battery. Typical uses. They're available in all the sizes that we typically know. They're interchangeable with alkaline batteries in many applications and used in a broad range of different devices. And again, since about when I was living in Europe in the 1990s, I just couldn't buy the nickel cadmium batteries because the Europeans were pulling them off the market because of their environmental liabilities. They disappeared here shortly thereafter. Okay, so the batteries that are really interesting nowadays are the lithium batteries. The first lithium batteries were developed in the early 1900s, and some non-rechargeable versions became available in the 1970s. So these were typically batteries that were used like in photo applications for quick charging of flash units. And then the rechargeable versions of the lithium batteries appeared in the 1990s. And one of the great advantages of lithium is that it's among the lightest of all metals. You know, it sits right at the top of the periodic table of elements. And what that means is lithium batteries have a lot of power in a relatively small package and with relatively small weight. And there are many, many, many different chemistries that battery scientists are working with. And the ones I'm going to talk about, only 3 out of the many, are the lithium-ion batteries, the lithium polymer, and then finally the lithium iron phosphate batteries. So the lithium ion batteries are the batteries that you typically find in your laptop computer. The volts per cell on these is much higher. It's about twice what you see in a typical nickel cadmium or alkaline battery. So they range somewhere between 3.3 and 3.7 volts, a little bit higher when they're fully charged. And discharged down to about 3 to 3.3 volts. And I'll say a little bit more about how far you can take these batteries in just a few minutes. The discharge curve of these batteries is really interesting. So what happens is when you put them on a load, they tend to maintain their voltage for quite a long time. And then when they come to the end, they die. And you know, again, for the radio control modelers, that was really important because you know you're happily flying along thinking everything's hunky-dory, and then the battery just goes. And there's really very little warning when that happens, and I'll show you the curve that explains that in just a second. Charge types indicated here. Again, I'm not going to go into a lot of detail because of time. The point to make is that lithium batteries should be charged with chargers that are specifically designed for lithium batteries. Their power density is really good compared to the other batteries. So if you remember before, for the alkaline batteries, we were talking around 30 to 40 watts per kilogram. Here we've got 100 to 250 watts per kilogram. So big difference in the amount of power that's available for the weight of the battery. The lithium-ion batteries will tend to discharge if you don't keep them topped up over time. And their life cycle will vary depending on the type of the battery and again, how well you care for them. And most importantly, how far you discharge them whenever you're using them.
Now for disposal, there's not in these batteries not such a big toxicity liability, and often many of the batteries contain valuable metals like cobalt, and so there's a real interest in recycling these batteries because the metal that's in them has a lot of value. So you'll typically see much more interest in recycling the lithium batteries just because of the value that they have for recycling. The typical uses for these things, they're used a lot, for example, in our cell phones and in laptop computers because they're lightweight, they're high energy density power source, and the way they're used is that many small batteries are connected in a parallel circuit because it's a more efficient way to put the batteries together to construct a battery for use and to generate their power. So, for example, this is a lithium battery. This is a battery that actually has 4 cells in it. So the 4 cells are wired up in series so that the total voltage here is a 14.8 volt battery. And again, very to the power density here, there's a lot of energy in this, and the batteries are all wired together, so multiple cells to create the form factors people are interested in. So I'll circulate that one. That's a lithium polymer battery, and I'll talk a little bit more about them in just a second. So they're used in portable devices, power tools, and oftentimes electric vehicles. And they're also the batteries that were used in those portable little skateboard things that were lighting on fire. We'll talk about the fire in just a minute. So the lithium polymer batteries, I've sent a lithium polymer battery around. There's some more lithium polymer batteries here that I'll circulate. Their nominal voltage is about 3.7 volts per cell. When they're charged up to 4.2, and again, they're fully discharged at 3 volts. And same discharge pattern that I talked about just a second ago. So discharge curve is flat with a sharp drop off at the end. Again, stick with the right charger. The power density on these things is even better than the one I just mentioned. So this is 150 to 400 watts per kilo. So a lot of energy jammed into these packs, and you can get between 500 and 1,000 cycles for each one. So on these batteries, I'll send these around. What you see on these is there's a discharge rating, a voltage and cell count, and a capacity. So this battery here, this is a Glacier battery. It says 3 cells. So it's a 3S battery, which means that the 3 cells are wired in series so that you get a total of 11.1 volts. It's got 1,400 milliamp hours, and it's got a 45C discharge rating. So 45 times 1.4 gives you whatever the math is on that. So it's a lot of power that comes out. So I'll just circulate these around. You can have a look at them, and you can see like this one is 15 C, 7.4 volts, 850 milliamp hours. This one is 7.4 thousand milliamp hours. So they come in all different form factors, shapes, sizes, and form factors that make them interesting for a whole bunch of different uses. So, and then when you see these things, as I said, each cell has 3.7 volts per cell, and there's a nomenclature that goes along with them. So if you have cells in series, the numbers of cells in series is indicated with a number followed by S. So a 2S battery has 7.4 volts, a 3S battery has 11.1 volts, and then when cells are wired in parallel, you'll see the number of sets that are in parallel, so 2P and 3P and so on. And their capacity is additive. So batteries in series, you add the voltage, and then if you take series wired batteries and put them in parallel, you increase the capacity. So you get these really wild and wonderful combinations like 3S 2P would have 6 cells with a nominal voltage of 11.1 volts and 2 times the capacity of a comparable 3S package. So again, these batteries, when you buy them, they come in all different combinations to kind of suit your needs. And I already talked about discharge rating and capacity we've already talked about. So typical uses for the lithium polymer batteries, these are the batteries of choice right now for the radio control flyers. So if and when I'm doing any radio control modeling, or if Jacob is flying his quadcopter, we're typically using lithium batteries. So that great big pack that's going around back there would be one that we would strap onto the quadcopter. Say again? And the little ones as well. So electric vehicles and so forth. Okay?
Hey, Leon?
Yes, sir.
Quick question. We noticed you have your main power terminals, and then there's another smaller connector with more wires.
Yeah.
So could you comment on that?
Sure, I will. And it has to do with charging and balancing the cells, okay? So what happens when you charge these things, the cells like to be charged and charged at the same voltage. So you're getting a little bit ahead of me, but it's a good time here to show you something. So this is a battery charger that I use for the lithium batteries. And this charger, when you charge it, the battery charging occurs through this hookup here. But then what you do is you hook the battery to this. Sorry for the microphone here. You hook it to this little device, which is plugged into the charger. And when this is plugged in here, what this does is this monitors the voltage in each of the 3 cells in here. So this is a 3-cell lithium polymer battery pack. And as it charges, it makes sure that the voltage in all 3 cells stays the same because of the difference in the internal resistance in the cells that will charge to a different voltage if you don't work to keep them balanced. So this little extra set of wires here allows you to make sure that your cells are balanced whenever you charge them.
And if they're not, then you're out of luck basically, because it's only monitoring the voltage.
Well,
It only monitors the voltage, right?
no, it monitors and balances, so it will discharge to keep the cells. Typically what it does is it discharges. If one cell gets ahead of another one, it will discharge that, or it'll drop the voltage a little bit so the other 2 can catch up. Okay, so it keeps all the cell charging balanced. And there's different types of balancers that you can get as well. Some are mechanical balancers. You just plug them in and they monitor the voltage, and they discharge the cells separate from the charger to keep the cell voltages balanced across 3, 4, 5, 6 cells, however many you may have in a battery pack. Does that make sense?
Yep.
Question you have?
Yep. Yes, sir.
Most batteries that I've dealt with and cells don't like being connected in parallel. These apparently are more tolerant.
They work. I don't have a lot of experience with them. Well, with these batteries, to address, I think one of the reasons why they do work is, coming back to Lee's question, is that when you charge these batteries, you have to be careful that you keep all the cell voltages balanced. So for example, I'll get to this battery here in just a second. This battery is a lithium, another lithium battery. This is an A123 style, so this is an iron-based lithium battery, and it has the same type of balancing capacity, but there's a circuit board that's been built into this thing so that when you charge it, it keeps all the cells balanced so that you don't run into those kinds of issues. So you do need to, I think you probably solve those problems through the balancing that takes place with the circuitry that's included with a battery like this. Okay, so this is a discharge curve for a typical lithium battery. So this is a lithium polymer battery that was discharged at 2.2. It's a 2.2 amp hour lithium battery, and I discharged this one at 2.2 amp discharge rate. What did I do with my pointer? Here it is.
So to the point I was making a little bit earlier, when this thing started off, it was about 12.5 volts, and the curve was fairly flat here, and you can see at the end, when it gets to the end, it just falls off a cliff. So you can use these batteries, and then when they come to the end, over the edge they go. And then with regard to discharging them, you have to be careful about not taking the batteries too low. So when you charge a battery, these lithium batteries, they're 100% charged at 4.2 volts. And gradually their capacity gets, as you use them up, the voltage drops. And you should really stop at about 3.7 volts discharge with these things, because if you go lower than that, you basically kill the battery. They don't come back and you can't recharge it. So when they begin to fall off the cliff here, you can see that I'm right at 9 volts here, so I stopped there. If you take the battery much lower than that, they don't survive. The other thing with these batteries, it's best if you're going to leave them sitting around is not to fully recharge them and let them sit on a full charge. They last longer if you charge them up, and then a battery charger like this will allow you to discharge the battery back down to a capacity of about 50 to 60%, which is where they like to be if you're going to let them sit around for a long period of time. So the big issue with the lithium batteries is lithium and water really don't like each other. So if you open up a lithium battery and expose it to the atmosphere, it'll go bang. So you really have to be careful with these things. So, and the other big safety rule with these is that when you charge them, you shouldn't leave them alone. So when I charge them, we drop them in an ammo box. So if they light on fire, they'll at least be inside the box. People also put them in flame-proof bags and that sort of thing. So I don't keep them in the house near the wooden walls and that sort of thing, and put them in an ammo box, particularly if I'm going to leave them untended. And the other thing is that you can begin to tell when a battery is getting near the end of its life. I decided to bring this one in as an example. So if I send this one around along with this one, you'll notice that this is really puffy. So when they get close to the end of their life, they generate gas inside the sealed pouches, and this is a sure sign that this battery is on its way out. So I would never put this on charge for risk that we might have a little fire. So I'll send this one around, and you kind of give a little squeeze, and you can get a sense for a battery that's really it's perished. So wouldn't use that anymore. Let's see what I did with my thing here.
Except as an example.
Say again.
Except as an example.
Yes, sir. Computer fires, you know, lithium batteries going off in computer fires. So this is an example here, and then Bill might want to comment on this. The 787, when it, the Dreamliner, when it was introduced, they were using lithium batteries in it, and they were having some lithium battery issues, and I guess they were having a few fire problems that Boeing had to work out. So they're great technologies, but you have to treat them with respect. So to get rid of these batteries, the best way to get rid of them is to drain them down, discharge them as far as you can, and then the recommendation is just to cut the wires and kind of expose them and drop the battery in salt water so that it fully and totally and completely discharges. And once it's like completely and totally dead, you can drop it into the trash. So the last battery technology on the lithium side that I wanted to talk about is this represented by this battery here. This is the lithium iron phosphate battery. This is the kind of the newest technology. The brand name for this for the company that sells these things is A123. And A123 actually was a business that we worked with at Duracell that was making batteries for electric cars. So they're very high capacity, quite lightweight batteries. So this battery here is a 12 volt, 9 amp hour battery. So you can, there's just a tremendous capacity in this thing. So I was interested in this for parks on the air. You know, you can throw in your bag carrying one of these things, which I'll show you in just a second. So really nice technology. When you buy these batteries, this is from a company called BioEnno. I first heard about them by watching Ham Nation, and they're really great people. I called them up and got some advice on the battery, and they sent this out. You charge the battery here. There's a balancing circuit board that's built inside each one of these things, and then when you want to use the battery, it actually comes with the Anderson power pole on it, so it's all ready to go. So I'll pass that around so you can have a look at it. Self-discharge is minimal, 2,000 to 7,000 cycles, so it's got a lot of reuse capacity. And the other thing is that the fire liabilities that I just talked about, they don't exist with these batteries. So these are much safer technology to use than the lithium polymer batteries. And I expect we're going to see these batteries really taken off in the days ahead. So here's the power curve for that particular battery that I just sent around. So I put it on the battery tester. Just as advertised, it started off at a little over, well, it's 13.5 volts here,
again, you can see the discharge curve, it's just dead flat all the way, and again, like a typical lithium battery, when it comes to the end, it dies. And then the nice thing about this battery is that you can't read the numbers here, but it's rated at 9 amp hours. I got 9 amp hours out of it, so it works exactly as advertised. So again, great technology, lightweight, easy to carry on trips. You can also get solar chargers that work with them, so you can put them on a solar panel and charge them in the field. Okay, I'm getting close to the end here. I want to just talk one other thing about lithium. Lithium, as I said earlier, is when it mixes with water, it just lights on fire. So when lithium batteries are made, they're actually made in dry rooms. So again, when I was working in the Duracell business, we assembled lithium batteries at a manufacturing center in North Carolina. And this was a vast manufacturing facility where we were making these batteries in rooms that were practically at 0% humidity. So when you go into these rooms, you go in kind of through an airlock, and you got to keep the water out because the lithium itself comes in these nice little rolls here, and if they get any water on them, those will catch on fire and create a real mess. So making lithium batteries is a real challenge because of the instability of lithium in a water atmosphere. Okay, real quick, I'm just going to talk a little bit about lead acid batteries. They've been around a long time. They're sort of the, yes sir?
What was the energy density on the polymer batteries?
I'll come back, and I didn't put a number on it. It's quite high though. So I don't know what that battery weighs, and it's 9 amp hours, so I have to do a quick calculation. I looked for the number, but I couldn't find a number to cite here, which is why I didn't put it on the chart. But there's a lot of juice for a battery that's pretty light. And I'll have a comparison with the lead acid battery here in just a second or so. And you'll see why I like them. Okay, so the volt, they have about 2 volts per cell, and so when you put the 6 cells together, you end up with a 12-volt battery. The discharge curve on these things, I'll show you in just a second, is a gradual slope, so when you run them down, the voltage gradually decreases over time, and once you reach the end, you should stop before you kill the battery. And again, I'll talk about that voltage in just a minute. They're really heavy, so they're 30 to 40 watts per kilogram compared to like 400 watts per kilogram for the lithium batteries. So they're really heavy for the amount of power that you get out of them. And then if you just leave them sitting around, they discharge. So if you have lead acid batteries, you really need to keep them on a charger. Just let them float on a charger, or you need to top them up every once in a while, because they'll discharge and then they'll spoil on you. 500 to 800 cycles, so not as much as you get out of a lithium battery. You'll get a couple of thousand cycles, so they claim out of that battery that's going around. And again, disposal is an issue. I'm sure, as you all know, they're filled with lead. Lead has a lot of environmental liability, so they need to be properly dismantled and recycled at the end of their life. Now, they tend to be, the one good thing about them is that they're cheap. They're not very expensive. Lead's not very expensive, and the technology is easy to put together. They're widely used, even when surge current is not important, or when other designs could provide higher energy densities. The large format designs are used for all kinds of stuff: backup, solar energy storage, situations like hospitals, standalone power systems. So and if you remember that pie chart that I showed you, they're just used everywhere for backup systems and, like I said, solar systems and so forth. So now the interesting thing about sealed lead acid battery capacity is that what you think you got isn't really what you have. So for example, the typical amp hour rating that's printed on the side of the battery refers to, it's like everything else, squeezing the last drop of power out of the battery. So the amp hour ratings are based on starting with 100% charge and then dragging the battery down to this 10.5 volts. Now, if you do that, if you run your battery down, your sealed lead acid battery down to this 10.5 volts, you will very quickly destroy your battery. It turns out with the sealed lead acid batteries, about as far as you should go on a regular basis is to drag it down to 11.9 volts and then stop. So what that means is that for example, with either of these sealed lead acid batteries, this battery is labeled with a capacity of 2 amp hours, and this one is labeled with a capacity of 5 amp hours. I'll show you some charts that actually show that you get about 50% of that. So you get about 1 amp hour out of this one and about 2.5 amp hours out of this one. So if you're buying sealed lead acid batteries and you want to know what capacity you're really going to get, you just take the number on the side of the battery and divide it by 2. So these are sealed lead acid batteries, and just pass those around as examples. So I use these batteries for emergency purposes in my shack typically.
So this is a discharge curve on a 2 amp hour battery. So the battery that Don has right here, so the discharge curve on that battery is shown here, and you can see when you plug it in, it drops down to about 12.5 volts, and then has a relatively flat curve, and then it stops.
Just move this thing. Raise it up.
All right, we'll try that.
So it drops down, and then when it reaches this 11.9 volts that I mentioned to you, you end up, in this case, with about 1.3, 1.4 amp hours. So on the side of the battery, it's stamped 2 amp hours, so to the point that I was making. And then on this one, the 5 amp hour battery that is over here this is the discharge curve for that battery, and you'll see that it comes down to, that's 2.135 and 2.372, so it's 50% of the 5 amp hour capacity that's stamped on the side of the battery.
And then this is just a comparison between the two, compared the 2 amp hour and 5 amp hour. Again, in this case, we got about 1.4, and here we got about 2.5. Very similar types of curves. They're just flat, and then when you reach the voltage, you gotta stop. So then to do some comparisons here, so if you compare a lithium battery with a sealed lead acid battery, so the lithium phosphate battery, that the bioenno that's going around over there, the parameters on it here cost about $100. Its weight is 2.6 pounds. You can see the size there. Its maximum continuous discharge is 18 amps, so you can hook it up, run it at 18 amps without hurting it, as long as you stop at the right voltage. And you can get a peak pulse out of it of 36 amps for 2 seconds. So they don't like to be, this particular battery doesn't like to be discharged any more than that for a short period of time. Anyway, you compare that with the PowerSonic battery. So this is a 12 volt, 18 amp hour battery. So for a similar capacity, that sealed lead acid battery is half the price. It's $46. And but it weighs 10 pounds more. So if you want to carry it in a backpack, that's a lot for the equal weight. It's a lot larger. You can get a higher amperage draw from it if you want. Peak pulse is 180 amps for 10 seconds, but you can't take a deep discharge on this particular battery. So you kind of, you can play the game and twist it back and forth. Yes, sir. 5 minutes, okay, almost done. I'll skip the landfill piece.
Chargers, my message with chargers is just to use the right one for the right batteries. Test equipment, all of these discharge curves that I showed you are done with this device right here. This is a really cool device from West Mountain Radio. Comes with a little piece of software. You hook the battery up here, and this gets plugged into the USB port of your computer, and you can generate all these curves, and it's really fun to keep track of your batteries. You can see what happens to them over their lifetime, and you can see whenever they begin to decay. Like for example here, this is, as I've already talked with you about, you can measure capacity, monitor over time, and you can compare batteries. So, for example, I already showed you the comparison between the nickel metal hydride and the alkaline batteries. This is one I like right here. So this compares 2 5 amp hour batteries. So I was wondering why one battery wasn't lasting very long. So I put it on the charger. So This is a good battery that has about 2.3 amp hour capacity, but my 5 amp hour battery that wasn't lasting very long, you can see that its capacity was about 1.1 amp hours. So this guy is on his way out. So it's a tool that we can use for that. Here's another one. I had another one of these, these 2 amp hour batteries. I compared 2 of those. Again, one wasn't performing real well, so you can see this is the good one, and this is the one that's on its way out. So it's a real handy tool to help you test your batteries and see whenever they're beginning to die. On safety, I'll just say that, you know, these are little boxes that are filled with energy, and if you're not careful with them, you can really hurt yourself. So, you know, don't short them out, because you know, a screwdriver dropped across a 12-volt sealed lead acid battery will make a big noise. And then the other thing is that the electrolytes in some batteries are really caustic. So I've ruined a couple of pairs of jeans just moving batteries around. There's a shot full of holes whenever I'm done. So don't wear metal jewelry, don't smoke around them, because when you charge a sealed lead acid battery, they do release hydrogen gas, and hydrogen and oxygen go bang as well. So you just need to take safety precautions. Last slide here is about battery advancements. Like I said, battery technology is limited by the size of the can and the periodic table of elements. So developing new battery technology is really a tough thing. This is the history of the development, and it's real consistent with what I talked about here this evening. We started out with lead acid, nickel cadmium, nickel metalhydride to lithium ion, and we're now into the lithium metal batteries, like these lithium iron phosphate batteries, and so this is where the technology is going to be developing going forward. So, all right, and that's my. All right.